Good evening to all and welcome to the Bhoo-Mandal talk series. Today's talk is by Professor Vijayan Asari from University of Dayton, Ohio, and the talk is on addressing the data desert and aerial LiDAR. This talk series is organized by IEEE-GRSS Bangalore section, and this particular talk is co-organized with the IEEE-GRSS Kerala section as well. So regarding the talk series, this has been initiated by the chapter since July 2020 during the times of the pandemic. So we had this as a public talk series where experts give talks on all topics related to geoscience, remote sensing, earth observations, etc. And most of the times we have looked at focusing on problems related to India, but today for the first time we have Professor Ashari, who is an international expert. Let me just give you a brief overview of what IEEE-GRSS itself is. This is a 1-minute promotional video that is available in the IEEE-GRSS archives. So GRSS is short form for Geoscience and Remote Sensing Society. This is a dedicated society for remote sensing professionals for career development, networking, etc. So I'll just play the video for a minute.
G
R
is
S
is the IEEE
Geoscience
and Remote Sensing Society.
Our mission is to build a community of researchers and practitioners by means of knowledge sharing and scientifically rigorous dissemination of the latest advancement in remote sensing.
The technical committees are really meant for doing the technical outreach to other parts of the research community and industry.
We want to inform our members and reach different communities via different channels, like for example social media, journal, and especially education.
At the moment we have more than 60 chapters and 20 student branches all over the world.
I love GS family very much and I'm very honored to be the member of it.
Being part of GRSS allows me to be a better researcher and professional, improving my skills and knowledge to do a good job. Come and be part of this great family. Ciao!
So let me start introducing the talk for the day, and then after that I will introduce the speaker. So today's talk is on addressing the data desert in aerial LiDAR. And this is work done at University of Dayton, Ohio in the Vision Lab run by Professor Ashari. And this is the work jointly done by Nina Singer and Professor Ashari. So in this talk, Professor is going to talk about the DAILS dataset. DAILS is a short form for Dayton Annotated LiDAR Earth Scan. This is by far the largest available aerial LiDAR dataset, which is annotated and is available for the public for implementing semantic segmentation tasks. In that regard, it is a benchmark data. And through this talk, Professor is going to talk about the challenges involved in working with aerial LiDAR data, most probably with related to the data acquisition and preparing the data as a benchmark and how it can be made available for these benchmark tasks different from the terrestrial and the mobile LiDAR scanning data. Now we have with us Professor Bharat Lohani, who is actually leading the efforts with the DST, that is Department of Science and Technology, for the Bureau of Indian Standards, where he is leading the committee to recommend the standards for aerial LiDAR. So I will invite Professor Lohani to speak for a couple of minutes on motivating why this is a pertinent problem that we should solve in the Indian landscape. And we will learn a lot of lessons from Professor Ashari on how he could come up with this data set, and we could probably do similar work in India. So after Professor Lohani.
Okay, thank you very much, Professor Jayan. And I was thinking that I will talk to Professor Asari. Okay. So anyway, we have been working with the LiDAR at IIT Kanpur for quite some time. And in fact, we started working in this domain. And since 2002 in IIT Kanpur, I started working in this domain from 1997 onwards with the aerial data. And yes, as the topic of this address is data desert in aerial LiDAR, very pertinent topic. And this was also a reason for driving some of my research, because in India, LiDAR data were not at all available, not at all. And I chose to do research in the area of LiDAR, but there were no data. So we faced very typical problems, and we tried our best to collect the data. So we were successful in collecting the data, generating the data for IIT Kanpur campus in 2008. And that served some of our research requirements. Also, we then thought of, why not to simulate data? We started simulating data. So we have now our Limulator, which is the LiDAR simulator. The version 4 is coming up. And the good thing is we are in fact simulating data which are similar to the DALS data. And rather we are taking the DALS data as the, one set of the data, which are the data coming from the field, and similar kind of terrain, similar kind of object, same data density, same sensor, 1560 from Regal, with those 5 flight lines and 75% overlap in the swap, with the same data density. We are simulating that data because we thought that we would like to address how by mixing the simulated data with the real data, both labeled, because the simulated data are automatically labeled. So there is no expenditure, no resource that is required to label those data. So we want to test this hypothesis, how we can increase the accuracy by bringing our data augmentation through the simulation process. So currently the simulation that we are doing is for the aerial LiDAR, mobile LiDAR, terrestrial LiDAR, all kinds of things. And we have a very generic simulation engine ready with us. So this particular work on the DALS data is going on right now. Now, this is again talking in terms of the entire India, because I have been in the LiDAR research, LiDAR industry from early 2002, as I said. Considering this data desert in India, we thought, okay, why should not we start doing something in the field? So from IIT Kanpur, we started our company. And Geno India Private Limited, a company that we started from IIT Kanpur in the field of LiDAR research, in the field of LiDAR solutions, started working with the terrestrial, mobile, and then the airborne case. So today, our company is leader in this in India, and we have already generated aerial data for around 80,000 square kilometer in India, which has a couple of cities, a couple of irrigation sites, a couple of rivers, both sides of the river, 10 kilometer, both sides. So that is something which is happening. And then some more companies have joined, and some more companies are now also collecting the data in India. One very good thing that is also related to the data desert in India, that was before 15th February 2020, around a year back. LiDAR data or the high resolution data were considered to be kind of very classified data in India. And in order to generate that data also in our startup, we had to take multiple permissions, which would also take some time, 7-8 months, 1 year kind of time. And then once you generate the data, there was no possibility of sharing that data with the people, dissemination of the data with the people. But on 20th February 2022, 15th February 2022, India has come up with a new geospatial data guideline. And as per that guideline now, data of any accuracy of any kind can be generated by Indian entities anywhere within India, except few areas, which are the sensitive areas. And there will be no restrictions. So this sector has been completely deregulated. So today, for example, Professor Ramaya, she has captured the data of a city for the research, and anybody can capture the data, and the data capture has become very fast for the companies also, which used to spend 7-8 months time to get the permission. Now they can generate the data very fast. Another thing of this data policy is all the data which are generated using public fund will be shared with all government users without any fee, with private users also with some nominal fee. So like in many other countries, the data is being considered as the public good. So the data will become available now for the researchers, and whoever is capturing the data will be sharing the data. Currently, we are working at the central government level in order to arrive at that framework, how this data will be shared, how the metadata will be stored. So we are working on that line. So soon there will be a very good clarity. Soon there will be a portal, and the metadata will be uploaded on that portal. The request will be made, and finally the data can be downloaded. So yes, I have suffered a lot this data desert in India for LiDAR. And fortunately, yes, it took time, but today now the situation is becoming better. And even today, Professor Asari, we are discussing now India-wide elevation program. Like we have one in USA, the 3DAP program. So similar program we are discussing, and we are trying to create the right ecosystem, strategic document, working with the USGS in these lines. So this data desert in India, we are going to handle it. And the good thing is for the researchers like us, all the young researchers who are there in India, they will be able to get the data and work with the data. Yeah, thank you very much. I think good enough from my end this time. And thanks for giving me this opportunity to talk about IIT Kanpur, our background, and also what is happening in India. Thank you.
Thank you, Professor Bharat. So I'll introduce. So yeah, so we have motivated the problem of the data desert in India with respect to aerial LiDAR right now. So with that, I will now introduce the speaker of the day, Dr. Vijayan Asari, who has kindly accepted our invitation to enlighten us about his experience in preparing and disseminating the Tails dataset. So Professor Ashari is a professor in the Electrical and Computer Engineering and Ohio Research Scholars Endowed Chair in Wide Area Surveillance at the University of Dayton, Ohio, USA. He is the director of the Center of Excellence for Computational Intelligence and Machine Vision Lab, which is called the Vision Lab. Dr. Ashari got his BTech from College of Engineering, Trivandrum, MTech from IIT Madras, and then subsequently he did his PhD as well in IIT Madras. Subsequent to that, he worked in Singapore for a few years, both at NTU and NUS. And then he moved to the US and joined Old Dominion University in Virginia as a professor. After he worked there for a decade, he moved to University of Dayton, and he has been there since then. So his lab specializes in object detection, recognition, and tracking in wide area surveillance imagery captured by visible, infrared, thermal, hyperspectral, and LiDAR sensors. His research activities include 3D scene change detection, automatic visibility improvement of images captured in various weather conditions, etc. He holds 5 patents and has published very widely with around 700 research papers in his kitty. And he has supervised several PhD scholars and MS thesis in the last 2 decades. He has also received several awards for his work, both teaching, research, advising, technical leadership. He is a senior member of IEEE and an elected fellow of SPIE and member of several international societies. So we welcome you, Professor Ashari. It's our pleasure to host you today. The stage is yours. Thank you.
Thank you very much, Professor Jaya and Professor Lohani and others. Ramya, Ramrao, I mean, Gurudatta, yeah, Shamlal, and see, I think it's a great opportunity for me to meet with all, before presenting, and actually more than that is meeting with and experts in India. And it's really great to see the leaders in this particular area, and also possibility of communicating further in our joint efforts to make something really productive and effective in this area of research. So that's the motivation. Basically, when I had this invitation from Professor Jaya, actually I was so happy to accept it, because it is more than a presentation. Actually, it's an opportunity to meet and collaborate and establish some relationships. That's the idea. Anyway, so thank you for the organization and organizers of this particular Bhoo-Mandal talk. Looks like a great opportunity for several people to come together and then exchange their ideas, and who knows, I mean, it's a multiple concepts and philosophies will come together, will make the system more stronger and effective, right? That's what exactly the motivation of these kind of forums. So I really appreciate inviting me to this and giving me the opportunity to present. Okay, so what we did is a small, contribution to the field. I'm so happy to hear from Professor Bharat Lohani that this data is being widely used. That's what some of the important aspects. In that case, we have a little bit more pressure, Professor Lohani, to make the data more wider and more broader, because I'm going to present what we did. Actually, we can do way more than this, and maybe we will be able to make an effort together. I mean, so it's important. And I'm happy to hear that actually last month the government of India has given effective orders to have data captures and the data annotations and make it available to the public for research and even beyond that. So in that case, that is absolutely a great initiative. So the title of the presentation is basically introduce the data and the what exactly is that. I mean, most of you know about this data, but I'm going to tell you the history of this data. So before actually going into the real data and data history, I wish to say where we are standing at present. The University of Dayton Vision Lab is a center of excellence. Actually, the activities are pretty much same as what we all of us do. I mean, basically the data exploitation strategies from data acquisition to the decision making. But in our group, actually, the main motivation is go and basically to exploit the data. That is the central part of the block or the pipeline, processing pipeline. From pre-processing, that's one of the aspects which we need to do. No matter what data is, actually, we have to make sure that it is effective to further feature extraction and information extraction, and then classification and decision making to make appropriate decisions as and how the project is defined. Project means we are all working, I mean, basically on funded projects, so without funding, there is no research, so that's what the objectives and goals of these projects are actually determined first, and then we define the processing strategies based on that. So we have several research groups in our team, from the media processing, pre-processing onwards to the wide area surveillance. That is my main job of moving to Dayton, because of they created an endowed chair position here on wide area surveillance. And then we have a lot of activities on biometrics at different perspectives of biometric applications. And robotics, of course, vision-guided robotics, and mobile robots, and aerial. And then comes our area, perception beyond the visible spectrum. That's a place where we are actually talking about the different sensors and sensor modalities. And then there is another group, a small group, working on brain activity analysis that's actually extracting or collecting information from brain, like brain waves, electroencephalograph data, and processing exactly the same perspective of the data processing strategies which we use for everywhere else. And objectives and goals to be met, and then we define the processing pipeline based on that, and then take the decisions as and how the project defined. So that's what exactly the story of my lab, basically the multiple groups and several researchers are participating in this. And when we go to the DAILS, Dayton Annotated LiDAR Earth Scan, I mean, so we named it like that. This data, basically, when we started, because of the wide area surveillance initiative here in this region, we are working closely with the Air Force here, and then there is a lack of, as Professor Lohani said, a lack of data available, I mean, existing data. So we found a data source, which is totally unannotated data source in British Columbia, Canada, the western part. And then the data is available, but it's not annotated. So we thought, why not we use this data? And we contacted them. They said, okay, we can provide you the data, but it's all your job to annotate. And then we negotiated with them. Okay, if we do the annotations, okay, we can do it, provided we should get the right to make it available to the public, the researchers in this particular field all over the world. So we had agreed upon that, and then we have the permission to distribute the data once we annotate. So we actually selected a small portion. So that's what exactly I'm going to tell. We selected only 40 tiles covering about 10 square kilometer area with a density of about average 50 points per meter. That's the data which we received from British Columbia team. I'm going to tell the details of the team later. And we, from this 40 tiles covering about 10 square kilometer area, we have about 500 million points. We hand labeled them. And basically of 8 categories, from ground to vegetation, poles, fences, power lines, trucks, cars, and buildings, because we selected these a little bit of vested interest, because our wide area surveillance research with the research Air Force Research Laboratory here in Dayton. And so we selected those items and objects and so on and so forth. We can definitely go beyond that, because there are so much details available in the original data, and we have the entire data with us. If we go for, this is very too basic for a team like this, because everybody is very familiar with that. So introducing point cloud is to this team is not the is a right word. Anyway, we have, as all of us know, there are 3 different, Professor Lohani was also mentioning about that, aerial, mobile, and terrestrial LiDARs available, but we are focusing, this data is for aerial LiDAR. And from the LiDAR perspectives, and these principles are also not right, I mean, the introduction, because everybody knows about this, basically how LiDAR works and how data is being captured, and what are the applications, and so on and so forth. And basically, again, all of us know that these processing LiDARs with the deep learning algorithms and strategies are going to be very difficult, because of the unstructured type of characteristics of this data. So we have to be we have to develop our own strategies to to process this data in a way which we need, or to meet to the goals and objectives of our project. So to basically to detect and classify the objects in the scene, whether it is a terrestrial LiDAR or mobile LiDAR or any aerial LiDAR. So this is an issue for us, but we have strategies to solve. All of us working, in this area know how we need to handle this. Two examples of aerial LiDAR data and the ground LiDAR data. So basically, ground LiDAR is becoming very popular nowadays because of the autonomous vehicles, and all that is becoming one of the most promising products in today's world. So because self-driving cars, you need to have this distance measure assessed objectively to this particular way. So LiDARs, very cheaper LiDARs are available for ground captures, and very fast and real-time operations are possible nowadays. And so this LiDAR area, research area is progressing exponentially. There is no doubt about it. So no wonder why this area is becoming more popular everywhere, all over the world. And so autonomous vehicles are one of the most important outcomes recently, or products with these recently using these LiDARs everywhere, all the time. So why this data set? So if you look at the LiDAR data set available, for example, the aerial LiDAR data available, we have only two data sets. We found only ISPRS data beforehand. There were only 1.2 million points available, and then we cannot do a lot of, there are 9 categories, but we cannot do a lot of research with the different perspectives. And also in a real life environment, we need to face a lot of perspectives in the backgrounds and environments and so on and so forth. In that case, we found it's difficult to move forward without having the data. So what we did is, we have a LiDAR, we go for capturing data. That's not an easy task for a small laboratory like or research center like us. So in that case, we want to train the systems with a large amount of data. So we searched and found this data available there, but it's not annotated. That's the story behind the DAILs. And mobile LiDAR, there are several data sets available, but it's not, it's one actually. Paris Lilly is providing about 143 million points, and there are data which is providing up to about 300 million points with the 22 categories and so on and so forth. The mobile LiDAR data sets are pretty much good, but there are and static semantic 3D provides about a lot of 4 billion points, but that is static, stationary data. But we need a aerial flying equipment capturing data, and then that's a real life application for us, aerial applications. So that's the motivation behind the encroachment into this particular data set. The data which we found is from the city of Surrey in British Columbia, Canada. That is the extreme west area of Canada. That is actually northern part of northwestern part of US, beyond the Washington state, and that's the area where British Columbia, that is Vancouver and the city. Vancouver is within the British Columbia area, but this data is captured at the city of Surrey, and we always thank in our website also we should thank the city of Surrey for generously providing the raw data all the time. So we did the labeling and distribution job basically. The data collection by the organization there, actually the city of Surrey, they used this regional Q1560 flow, and they captured the data, the whole data, actually, it is not 10 square kilometers. The data is available, 330 square kilometers of data available there. And what we did is we chose a very small area. I mean, so it is not, it's very small area. You can imagine, we chose only 10 square kilometers out of the 330 square kilometers of data available. So that means if we sit and annotate this 330 square kilometers of area, we can have a lot of information, a lot of objects, a lot of backgrounds, variations, varieties, and things like that. But we continue doing this job. For the time being, the Dales covers only 10 square kilometers of area out of this entire data set. Of course, as I mentioned, the point density is 50, average density is about 50 points per meter. And vertical accuracy is also very precise. I mean, relatively precise, 8.6 centimeter vertical accuracy we provide. And this data, the aircraft flew in all directions, and there is a 40% minimum overlap in this data, and they collected in 2 days. And the tile selection, what we did is the 10 square kilometer area selected. We chose the area using Google image as the references. What we chose is we wanted to cover all the 4 different regions, like rural area, suburban area, commercial area, urban area. So Dales covers all these 4 specific areas, which you might have noticed it clearly because of our interest in the project actually motivated us to cover the 4 different areas, where urban area building greater than 5 stories. Because in the city of Sarai, there are so many buildings, as I showed there in one of the slides earlier. So we have commercial area, means it is a lot of warehouses and office parks. So these are all selected based on the Google images as the reference. And point density, as I mentioned, that is the guaranteed point densities. That is the minimum we have 20 points per meter, but the average point density is 50 points per meter. So that is the situation. I mean, the status of the data, Dales data. This Dales, of course, actually it is provided by City of Sarai. It contains multiple returns as opposed to the MLS and the TLS data set. That's a mobile and a terrestrial LiDAR data sets. We did a small pre-processing before distributing the data because there were, of course, we can expect the raw data had a lot of noises, which we removed by a small basic algorithm. We automatically removed the points which are stray points, actually the points which are far away from the points of interest. So that way we removed the points, and that is noise points are, and then the pre-processed data is provided for other researchers, because the distributed data is actually a little bit of pre-processed, because there is no point providing the massive data with lots of noise and the space wise, and there is no impact. So we thought it would be always better to do this pre-processing and then provide the data. That's what exactly we did. So the strategies used for pre-processing is basically the distance from the object areas, which our objects of interest areas. If the points are far away, stray points, they have to be removed using a Gaussian distribution strategy, which we employed, and remove the points, stray points, and then the pre-processed data are provided to the public. We had a digital terrain model by employing a concept of progressive morphological filtering. That is actually, we have removed the sharp transitions in the points. So there is no point that, because it is considered as kind of a noise from our experience. And then we used the smooth transition areas are all kept, and then the data provided is actually the filtered data. So the annotation strategies is all manually annotated 500 million points. Actually, we used the surface normal concept for pre-estimating the surface areas, and then we used from there to the different categories of objects. Of course, most of the points are all ground points. So we don't count the ground point as an object. Actually, that is a base. And then we have the other 7 classes: the vegetation, cars, trucks, power lines, poles, fences, and buildings. And these 7 items, other than ground, actually we selected with the objectives in our mind, a little bit of the interest to the project which we were involved in. As you can imagine, the number of points for all these categories will vary significantly. For example, the poles, we can expect only a few points for the poles, but at the same time, for a building, we'll have more points, and vegetation, there will be more points available. And depending upon those, and the power lines, it's a narrow point stream. So in that case, we need to make sure that there is a big class imbalance problem which we face in the processing strategies, which we need to resolve. That's one of the again challenges in this particular data set. It can be it is the challenge in every data set which we can imagine when we select the objects of these kind of ranges from poles to buildings, So the region where we covered is actually the northwest point of actually not United States. We can see the Washington state is this extreme northwest corner of United States, and the Canadian, the British Columbia is just north of that, the neighbor of this Washington state. So the region where we cover is actually the region 10, that is 120 to 126 degrees. So that's the region where this particular data is captured. That's a region where the British Columbia or the city of Surrey within British Columbia is situated. And in our distribution strategies, we have made the data available to this go-udayton.edu Dales 3D website. And there is a small form, as you know, available to request the data. Once this form is filled up, and you get the permission to download the data. So far, for the last 1 year, 1 year, maybe a few more months, to more than 2,000 downloads we recorded. That means this aerial LiDAR processing is going on really well all over the world. I mean, so it is in this particular small area of research, actually, this is a significant amount of downloads which we can expect in the aerial LiDAR area itself. So because most of the LiDAR researches are going on in the ground LiDARs, but nowadays, actually, aerial LiDAR research is also progressing significantly all over the world. So this is the statistics of our distribution. And also we license to MATLAB for their deep learning toolbox. So they are providing this Dales dataset as the basis data for aerial LiDAR processing deep learning toolbox of MATLAB. And depending upon this Dales object statistics, point statistics, you can, as I mentioned earlier, excuse me, earlier, the number of points, the ground, we have points, we distributed the points into about 70-30 kind of ratio, but not always true. Average is 70-30. But ground, you can see the test data is actually number of points in the testing is actually marked as blue, and then the red indicates the training data. If you consider only the training data itself, you can see, I mean, from the object vegetation, 121 million points available for training. At the same time, poles have only 0.28, 280,000 points. So that's the disparity in the number of points available for each category. So that's a class imbalance problem for deep learning. So we need to resolve it. We have some technology which we also proposed, and all over the world there are researches going on to resolve the class imbalance problem, and here it is significantly large. So definitely all of us have to pay attention to resolve this particular issue in aerial LiDAR dataset, because when we are looking from aerial, I mean, if you are looking at a pole, it means we will get only a few points. At the same time, we look at other objects, there will be a lot of points. So definitely it's a natural issue in aerial research, aerial vision research, and then we will have, or we have some kind of solutions, but not ultimate. It's moving forward. And this is the benchmarking results of the input point cloud here, and after processing, it provides the markings of all the object point categories. It's a point-based labeling, and this "What's the Point" is the title of a paper which we presented to the Washington, D.C. This is the equivalent output point cloud obtained from there. And so moving forward, we have an evaluation metric. Not normally, every one of us use this overall accuracy and mean IOU and the class per class IOU. So see, if you consider the overall accuracy and mean IOU, will get the accuracy measures appropriately provided. So what we did is to distinguish the performance of each algorithm, we defined a new metrics called class consistency index, because we need to know how effectively an algorithm performs well for these multiple classes with the different number of points available for each category. So in that case, some algorithm performs really well for some categories, some the same algorithm may perform very bad for another category. So that's the variance in the detection range, detection accuracy variance, that is a sigma square, and the ratio of sigma square to the mean IOU, and then the complement of that. That's the class consistency index definition. So that provides the effectiveness of an algorithm for all the classes. As we can see in this particular table, we chose for benchmark, we used the 6 popular algorithms: KP-Con to PointNet++, ConPoint, SuperPoint, CNN, ShellNet. And we found that KP-Con performs really well, better than all the other algorithms, and we can see the accuracy for the poles category. KP-Con gives an accuracy well about 0.75 compared to others. So the range for ShellNet, for example, it ranges from 96.4 to just to 20% accuracy. So that's the range of the ShellNet. At the same time, the range of KP conveys 97.8 to 75. So that makes, or fences 63. So that is the range for KP convey. So the variance in the accuracy, that is what exactly used for determining the class consistency index. If you look at that variance marked in this particular case, the range of accuracies for KP convey is way better than others because the range is less. And we used that as one of the measures to assess the effectiveness of an algorithm, which is actually well received by the community. Again, the robustness is also measured in terms of the class consistency index to the mean IOU. So we can see the robustness is going into the KP con is located at the most robust area compared to others. So we give an A plus for the time being, maybe A for KP con compared to others. And this actually is the problem where we found the class consistency index improvement is one of the motivations where we developed, we try to build a little bit of improved architecture for this purpose. So that is after all the benchmarking, one of the main takeaway is actually current semantic segmentation network is struggling with the scaling of different objects because of the number. Scaling of number of different objects means the size of the object, which gives you very limited number of points, and so on and so forth. So we came up with a kind of a architecture, a multi-level focusing network for revisiting feature layers. Revisiting feature layers. Actually, the concept is the human visual perception analysis concept. If we look at a scene, if we can see a lot of points, our attention to that region will be less when compared to we look at a point where an object where only a limited number of points. It's a small object which we are going to determine which or detect which object is that or recognize which object is that. That means we pay, knowingly or unknowingly, we pay more attention to that particular spot. That's the philosophy. That means we name it as look again. So look again, that is a second look. Look again, that's what I termed it as look again, but my student termed it as second look. So that means every point actually object which we want to see, because it is a small object. It is exactly same as when we use in a visible spectrum image when somebody is standing underneath a shadow, and at the same time another person is outside the shadow in a bright area. We will be knowingly paying attention, more attention to the person who is standing underneath the shadow, because we can get the features of that person only through more attention there. So that is the second look, or the look again concept, That's what we used in this building this particular architecture. So if you look at that concept of architecture, it's actually using a inverse pyramidal shape. It's slightly different from the conventional unit. Here, actually, we use the features of all the previous layers, and we concatenate the features to make a large vector size, a feature vector, in order to do the classification. There, we also introduced some kind of a feedback there. See, the focused kernel point convolution concept is introduced. There, we have multiple rounds of looking. That is the place where we are looking again. That is, looking again means the FKP is repeated multiple times by introducing 3 hidden layers. That is, we look again means we are processing it again and again and again in order to go for extracting better features And because of this recursiveness and also the residues. Residues means the multiple residues coming from the previous layers and the dense nature of the system. So there are three concepts introduced in this one: the dense network concept, and then the recursiveness, and also the residues. So all these three put together is supposed to give a better result. That's the idea of the new pyramidal architecture, pyramid point. So we named it as pyramid point, and then it is pretty much received well, and the classification accuracies are better. I don't want to say extremely better. So it is better than the other state-of-the-art algorithms. These are all the results we received, and the results which we found is the pyramid point provides better results in all the categories. The noticeable one is actually the poles and power lines, and but when we went for looking and again for the power lines and poles, we lost. We couldn't improve that significantly into the trucks, because when we look trucks again and again, it looks like a building, so that is another problem. But okay, but the result is slightly better than other results. We wanted that also in the 90s, and fences are also not significantly improved, but is improved pretty much when compared to the others. So we applied the pyramid point architecture for the MLS dataset, and we found that its mean IOU is better, but it's not very extremely good. So what we found is the pyramid point is good for aerial database, not for the MLS, and the TLS also not that really good. Only for the cars we got a better result in the case of a TLS dataset. So the pyramid point architecture which we built, we had some vested interest in developing that architecture, because we are dealing with the aerial data alone, not the others, but we wanted to test in TLS and MLS datasets, and it is not bad. Actually, it is performing reasonably well, but we don't see an improvement as we saw in the aerial dataset, where we have seen significant improvements. And beyond that, we did some extensions of DAILS. That is actually, we developed two more datasets, DAILS objects and DAILS viewpoints. First, I talk about the DAILS objects, where actually it is meant for instance segmentation. So instance segmentation means the class label. It's not the point-wise labeling. So the class labeling, that is one of the needs in our projects, where we need to have the instance segmentation. So we need to develop the instance segmentation data set. So we used the DAILS itself for classifying labeling the object categories as a single entity. Each object is identified as a ID is identified as a single entity and labeled. And this DAILS object is also available in our same dataset website. The comparison of the dataset DAILS objects when compared to other data sets are provided in this particular table, where we can see DAILS objects is actually provided for semantic and instance segmentation, but most of the other data sets are not for instance segmentation. There are only a few, but the number of points and points available for those are very, very minimum. So in that case, this DAILS object is also getting wide publicity, because object classification is one of the needs in our community, basically. And instance segmentation is basically used to the small algorithm, again, using the Euclidean clustering of all the points. And then for each clustered points are categorized into one object class. Some of the examples of, results, examples of this labeling is intensity data is provided at the leftmost column, and then semantic labels and the instance labels on the right side. And likewise, another example, a couple of examples I provided here to see the effectiveness of that instance labeling. And in instance segmentation, basically it's a close lookup at looking at the object categories. It is actually well labeled, and it's very, very effective and very useful for our community for further research. I think there are some categories in the number of points in the different categories, which we can see it is significantly varying, and number of points, the number of training points, test points, number of objects, and also number of points per objects. So it is basically these statistics provide a kind of a picture about the data set for different categories of or different classes of objects in our base. The evaluation metrics also slightly different. As we discussed earlier, semantic segmentation uses the per class IOU, mean IOU, and overall accuracy. Plus, to distinguish different algorithms, we use to the CCI, that is class consistency index. But here, instance segmentation uses the average precision and average recall as the popular metrics, which use the what is called the detection algorithms. So another important deviation is actually the Dale's viewpoints. As we know, when we capture the data from aerial views, we see a lot of occlusions. Because when we have a building and an object is on the other side, and when we go for, how do we get partially occluded or sometimes completely occluded? And some flights you will see that, some flights we don't see that. So in that case, is it possible for us to extrapolate the missing points? This is one of the objectives of our current research. Nina is actually defending her thesis on 11th of April. Actually, it's next Monday. And her basic motivation in that dissertation is actually filling up the occluded points, occlusion reduction in the aerial data captured by the aerial LiDARs. So in that case, how do we effectively provide the missing points, fill up the missing points? That means we need to use some kind of a generative algorithms. So occlusion reduction, that is her research topic we are currently doing. And I think next week she is presenting a paper, and a week after next she is defending her dissertation. So those information will be the topic which we are going to present next. So this is our current, or I put it as a future research. Actually, missing points due to the occlusions. How do we do that? But we need to use a generative algorithm there. So we developed a generative algorithm which will be able to fill up the missing points, because we have some kind of a training data which is captured by in all the viewing directions of the objects or region. So we use that kind of a reference, and then we use that concept exactly like initiating the generative algorithm. And after that, the algorithm generates and approximates and self-organizes by itself and fill up the missing points in the occluded LiDAR data. So we can see that the data captured at different viewing angles will be significantly different because some of the objects will be totally missing in the scene. So this is one of the needs in this particular area of research, because when we go for a test purpose for capturing the data, you don't get all the information when they fly. We cannot fly in everywhere, for getting all the points from all the directions. That's a tedious task. In that case, we need to have some kind of a generative algorithm to fill up the missing points so that we'll get a better data, reconstructed data, so that you will be able to do the processing in the subsequent processing strategies depending upon our goals and objectives, of course. And this is the filled up. See, the input is missing. A lot of points are missing. So is it possible for us to fill up the points with the missing in the occluded region? That is the current research going on. And another example for occluded points and full scene. So there is a significant difference in that. So we need the full scene in order to do the processing to detect and segment, whether it's a detection or segmentation process. So that is what. See, the occluded points are, I mean, if we send that point for our processing to our system, we will be missing a lot of information there. So in that case, we make sure that the points are reconstructed appropriately before sending to our processing pipeline. So that's what the research which we have just completed, and then it's going on. So that's all my presentation. So basically, Dales and its variants. Actually, we have the Dales objects and the Dales viewpoints are available in our same website, and made it available for the entire community. And we have covered only 10 square kilometers of area of the city of Surrey data, but we have 330 square miles of square kilometers of data available. We need to expand our annotations further. Plus, the most important thing which we consider, the Dales objects and Dales viewpoint data, which we will be able to use or develop algorithms. We means our community will be able to develop algorithms to fill up the gaps which we are missing due to the flying directions and locations, and the missing points should also be captured appropriately and accurately. So that's all my talk about, and the data is available at this particular site. Thank you
so much, Professor. This is an excellent, insightful talk. I mean, it just proves the point, right? You need a village to raise a child. So it's a similar thing like for working on aerial LiDAR point clouds. We definitely need expertise from so many different areas, and your expertise from vision is like adding to the gaps in terms of data dissemination and all of that. So it also goes back to the point that Professor Bharat had mentioned, right? So we have large amounts of data that is already captured, and some of these methodologies that we can work on can actually help in disseminating this data that which has been enabled by the data policy, the more open data policy that we have now. We can actually be using most of these data sets. So with that, this is like excellent work, and we have learned a lot today, Professor. So I leave the floor open for questions. If you can continue asking questions on Q&A, or if you raise your hand, we can also unmute and ask. Meanwhile, Gurudatta has a question here. So Gurudatta, would you like to ask directly?
Yeah, thank you. It was pretty much early in the presentation was the question. I saw that Professor was talking about pre-processing of the data. So I'm just curious, because I come from the industry point of view. I just wanted to know how exactly you pre-process the data. Did you use a particular software or a program to do the process?
Yeah, we developed a small software for computing the distance of our object of interest to the distance of the stray points. Stray points means single points which are not clusters of points. If it is a cluster of points, it is likely to be an object. If a point doesn't have any cluster, but it is actually way away from an object category, then that point is considered as a noise. So it is not deep learning algorithm. It's a very basic classical algorithm. The strategy which we used is actually the Gaussian strategy, the Gaussian network strategy. So if it is far away, and if that point doesn't have any neighbors, then that's a stray point. It's a noise point. So we eliminate that. That way we could eliminate a lot of single points, and that reduced the entire saving, the storage space significantly, because we don't want that much of area, that much of actually data has been cut off. Only the regions where the objects are situated are retained and provided as the database. It's a simple algorithm.
I just have one more question, sir. This one it just occurred when you were talking about the occlusion of data. So LiDAR by principle, it works on the concept of line of sight. So I'm just quite curious to know, like when you look at filling up the occluded areas through a generative approach, how effective would it be? Because we would never know what exactly stays in the shadow area unless we go to the shadow area and survey it directly.
So it's not completely occluded area. We have some prior information about the area from the imageries. So basically, that prior information we use for initiating the generative algorithm. And that, otherwise, we don't know whether there is a car on the other side of the building or not. We don't have any idea about that. So we need to have some kind of prior information about that. Then only we can regenerate and then add that into the points. Basically, this is not for 100% full occlusion. Basically, this is very useful for partial occlusions. If it is going to be partial occlusion, we can extrapolate to that object into that missing region. That's all.
Thank you, sir. Thank you.
We have a few hands raised. Professor Lohani, you want to go first?
Yeah, okay, thank you. Yeah, so thank you very much, Professor Asari, for a wonderful talk, so much to learn. And your pyramid architecture is really giving very good results. We'd like to see that further on that, because I can see visually as well as quantitatively the results which are showing are excellent for all the classes. And my question was actually same what Mr. Gurudutta was asking. And that was once we are trying to generate the points, the generation of a LiDAR data point from the ground depends upon what is there on the ground. For example, if there's a water body, no point will be generated in that area. So, but you answered it, that we are making use of some additional data, some ancillary information, which is coming from aerial photograph. In absence of that, it will not be possible, because in one of our papers, we also tried this, because we tried to generate some extra points for labeling using the existing label data.
Yes.
So there also we were wondering with this idea. So I have another question, and that is again related to something what we are doing today, because today we are working also in something similar for mobile LiDAR data in India, labeling it. So we want to create a library of it, because we understand in order to for the success of any deep learning algorithm, our data should be representative of the terrain. So if I train my data from the data from USA and now I start using it in India, the accuracy will not be there. So we are trying to generate some data for Indian conditions, and we are facing a lot of issues. Mobile data, of course, has got so many feature classes. We have around 75 feature classes that we have identified. It's a beautiful data, but we are really facing a tough time in labeling it. And we are going ahead with that. We have done, around 70, 80 files. We have done the labeling. Still, we are moving ahead with that. And we also want to share it with the researchers in India. That is the idea. So my question, I'm coming to the question now. Question was, for 10 square kilometer of the Dale's data, how much resource was required to label it? Because more or less the labeling is manual.
Yeah, actually, we have recently. I mean, this 10 square kilometer of area which we actually labeled manually.
Yep.
Okay, that was 500 million points, but that took a long time because there were no other resources available. Now we developed a semi-supervised labeling algorithm.
Right.
So what we do is we have the class information, the point information, semantic segmentation information. You actually run this into the raw data and get the preliminary results. That is actually we consider as a preliminary results, and use these preliminary results to go for fine labeling. So that's going to reduce the time. I think it's about 70%, 70 to 80% reduction in time. That is the algorithm which we are going to present at the SPI conference next week in Florida. Actually, the automatic labeling algorithm. In our case, at present, we released the algorithm, which is actually semi-supervised algorithm, which actually marks all the regions. And because once you have the region marked for an object, we can actually expand it to the boundaries so that you'll be able to mark the objects clearly. Okay, that is semi-supervised because we need further an improvement of our fine decision making by a human being, go through it and then see if it is right or not, because we cannot completely rely on the algorithm, right? Anyway, but we need to go only for the marked regions. It is already marked, so it is very, very effective in the labeling phenomena. Okay. Ultimately, what we want is a fully automated labeling algorithm. That will take some more time. Anyway, so the initial labeling of our Dale's 10 square kilometers, I think it's about, you asked about the time. I think it's about 2 to 3 months, I should say. Our people were actually spending a lot of time.
How many resources you put into it? How many people work for 2 months?
It's actually the graduate students and undergraduate students team.
I'm finding very difficult to motivate my undergraduate students to label the data.
small money from the project. Actually, we provide undergraduate research opportunity for the students to participate in the research. So we provide some hourly stipend for the students. And graduate students, of course, they are all full-time engaged in that. They need this data for their thesis and dissertations. And Nina is the captain here. Actually, Nina Singer. Her previous papers you might see Nina Varney, and she got married and she became Nina Singer. So the second data, Dale's objects, her authorship is Nina Singer. And Dale's, original Dale's, you will see Nina Varney. Both are same person, actually. So she is the key lead in this particular research. She's as you can see, she's the LiDAR person. Actually, she's the point of contact in my group, and she did a great job collaborating, bringing together this team and make them working. That is the motivation. Because I mean that needs a little bit of good collaborative mindset, so as we can see, to motivate the undergraduate and graduate students to sit together and then do this work. I mean, so she led that particular job anyway.
Thank you.
Full credit goes to Nina. Basically.
We will learn more from you. We'll interact with you more, and with Nina, of course. And soon she's going to be PhD also. She's Dr. Nina soon.
Yeah, she will be Dr. Nina in 11 days.
Great. Thank you. Thank you very much for wonderful talk.
Thank you, Professor Bharat. Ramya, you want to go next?
Yes, thank you, Professor. Thank you, Professor Asari, for the comprehensive talk on Dale's data set. So it was really inspirational. So recently, as Lohani sir was telling, we had acquired the aerial LiDAR data of Trivandrum as part of one of our projects. So that's covering almost like around 80 square kilometer over the city of Trivandrum at some 10 points per meter square. So that's the average point density, 10 to 15 points is what we get. So the same concern, my question was also on how did you manage to annotate the data, because that is the same problem that we are facing. Because when we, like one of our students is working on the semantic labeling of deep learning based architecture, we are using this RAND LA net for MLS as well as ALS data set. So we are trying to see how it works on both. So so as Lohani sir was telling, like when we use the objects from the Western world to here, Trivandrum is a very complex area with all the buildings covered by trees mostly, and it's a very complicated data. So the results we are not getting as expected. So that is why we were trying to annotate the data. I mean, we got the data very recently, maybe I would say like 15 to 20 days back. So it's a very, very recent data. And so I also, my question was also on how did you manage to annotate it? Like any software or anything was involved in labeling or annotating was the question. So that was
software is coming up as a public releasable software for semi-supervised learning, because without final human interference, I don't think we can release the data, because that's extremely important. We are not in a position to rely on the machine 100%, right? So, but it's going to help 70 to 80% of your time saving by using this annotation, semi-automatic annotation. Instead of going for semantic segmentation, you can apply the instant segmentation software so that you will be able to get a boundary of the region, so that you will be able to go and the person who is handling this will be able to go there and create the boundaries there. Just a fine tuning is the only one which we need to do by the human annotator. Before that, definitely, I don't recommend for the totally manual process which we did because there was no other way at that time. But the only algorithm which we did is actually on those time is the removal, the noise removal, and also for kind of a smoothing by the morphological filtering which we did, progressive morphological filtering strategy which we did, and after that it's completely manual annotation. So in this particular case, you can use that instant segmentation and get the bounding boxes so that you can go there and the human annotator can just fine tune at the region itself. That human interference is required at this moment, and I think people are trying for fully automatic annotation tools. I don't think it is available completely for our purposes, because reliability is more important before releasing the data, because it is going to be very critical applications, especially the aerial LiDAR. The applications are not only the ground-based. I mean, every application is important, but aerial, it is more sensitive, basically. I mean, so the other one is more secure. The ground LiDAR is more secure in that it's security, basically, for safety and security of our, because a driving autonomous system should provide accurate results. The other places, it is more on the sensitivities of the region. So, I mean, so definitely accuracy is extremely important. So without human interference, I don't recommend to release the data, but definitely you can use the automatic algorithms to the semi-supervised labeling strategies will be the right way to go, instead of starting from human annotators at all.
Okay. Thank you.
So,
And
but there is no other way. You have to spend time, right?
yeah, so
Trivandrum, I can imagine it's a very. I mean, all the cities. Think about Mumbai, So, I mean, it's much more complex, right? It's a.
Yeah. So yeah. So and one more small question, like this instance segmentation you were mentioning, this Euclidean based clustering. So that was like after the points were labeled, then
Cluster.
Euclidean was clustered. Then clustering was applied on top of it. Is it?
Right.
Okay.
Yeah.
Okay. Thank you very much.
Thank you, Ramya.
Thank you.
I'll now request Abin Bharat to unmute and talk. Ask your question.
My question is, how long it will take for inference 1 square kilometer of area LiDAR data?
Inference means the algorithm time or annotation time?
Annotation time.
How? That depends whether you go for processing and the semi-supervised way and then go for human annotation will be less time when compared to the complete human annotation, which is, 1 square kilometers. So at least a week time, I believe. Okay. And also depending upon your number of objects which you are looking for. What kind of objects which you are looking for, all depending upon our objectives and goals in that particular data base. In our case, we chose the eight objects because of our project objectives. So there is a little bit of vested interest involved in that. But I don't think in a city like Mumbai, we need to have what kind of objects which you are looking for. So there can be hundreds of objects, and there may be tens of objects, depending upon your objectives and goals in the project. Yes, that makes time exponentially going up because you are looking for very complex objects. Think about a city like Mumbai. Trivandrum is way more sparse when compared to Mumbai, isn't it? Yeah.
Yes.
Yeah.
Because here in myself, I had tried a small thing with using point CNN. So I used here a system GPU, NVIDIA Quattro, only 64 GB RAM. But it took around 3 to 4 hours for point CNN. That's why I asked.
Yeah, that's processing time is one of the tasks which we need to solve by the high-end computing systems. There is no other way. Yeah.
Thank you.
I think multiple GPUs will be the right way to go because
Yes. Thank you, sir.
Thank you.
No problem. Meanwhile, I have a question. So,
okay.
Professor Vijay's wonderful talk, and it really gave us very depth and breadth of this LiDAR point cloud processing and the issues, and also some of the strategies to make out so that a better way of LiDAR processing is handled. Thank you for sharing a really very insightful thing. I just had a couple of queries regarding this very same LiDAR processing. One is this: as we all understood that the processing of this LiDAR itself is really very tough, that even very small area of 10 square kilometers or let's say 20 square kilometers is again a task of let us say a few weeks, both human time as well as machine time. And if we see the present context of several projects which have been taken over a large area, including the one which we have all been following in Kerala, the Silver Line project, though some of their aims may be limited, but when we see our large city areas on the smart city, the requirement of this LiDAR based models, 3D city models and all other things by area is very, very large. Several thousands of square kilometers. And the limitations of challenges in terms of this thing are particularly the human challenge, both availability and the sensibility to handle, and the machine time. If we see what is the extent of, let us say, automation that we can expect within the next 2-3 years, so that some of the techniques and models developed at some location or some kind of objects and a model developed can be transferred to a different location. Perhaps the type of objects could be similar without much of this model making or with tweaking a little bit of model. So is such kind of scenario can we anticipate?
Yeah, model adaptation. That's what you are talking about, right? So yeah, it's a big area now going on in this particular, not only in this and in every other area. The adaptation of the models to different environment and backgrounds. So you can do that because adaptation algorithms are being developed nowadays. But you definitely need some kind of a preliminary information, maybe from other modalities, which will be able to utilize in that case for adaptation of the transformation of the objects category. See, I mean, Ramya was mentioning about the running algorithms which is developed for objects of object categories in a different country. It cannot be used for determining the objects in our place. For example, our auto rickshaws are not available in other places. So how do we get auto rickshaws to be? We need to train our system basically to this particular object category, which we will be able to see in our country. Now, every city will have thousands and thousands of auto rickshaws. So how do we? But in the automobile categories, you don't see an auto rickshaw in that in any other databases. So we need to have our own data set. So we need to adapt to that. So in that case, we need to retrain the system with this new object category. There is no other way. But see, the buses of different countries may look exactly same as the buses here, but cars look same. But there are some objects which are not looking exactly the same. Buildings, for example, there will be peak roof buildings and flat roof buildings and multiple shapes at the roof when we look from the aerial. So some countries you will see a kind of a Adobe type of buildings, so which is not available in a public database. Because public database is basically, for example, in our Dales is available from city of Surrey. They don't have any Adobe buildings. So how do we get the Adobe buildings to be captured? If you go to the New Mexican area and all that, you will see a lot of some cities have totally Adobe areas, Adobe buildings there. And this adaptation is a very important aspect, but algorithms are being developed for that. See, for example, even an animal, so the look significantly different. See, for example, elephants in South Africa and elephants in our country, actually, they're not exactly the same, but overall structure is same, but there are some fine adaptation required in a similar structure, similar category, similar object, but different objects, you have to have some kind of a algorithm to retrain the system with our new data. So this is depending upon the application which we are, or objectives which we have in our mind. So this vary from project goals, basically. It's a complex procedure. Even an algorithm trained well for Trivandrum may not run in Mumbai or Calcutta, right?
Yeah, that's that is challenge as an opportunity for research, but challenge for practicing.
Yeah, I had the same problem when we had a oil and gas pipeline search and rescue objective, intrusion detection. See, oil and pipeline right of ways are there. There will be parking objects, and basically by construction people, they, after completing their construction, they park this huge equipment on a free places, which is actually oil and gas pipeline right of ways. Underneath these free spaces, the pipes are going. If you are putting a huge equipment on the top of the pipe will break, and it may be a very empty area. The people know about this breaking of the pipes only after the neighboring trees are destroyed or the water is polluted and things like that. Otherwise, nobody knows. Otherwise, somebody should light it, so nobody is going to do that. But thing is, it's a very dangerous thing. Naturally, it is a very dangerous thing, but economically, these oil and gas pipeline companies, they lose a lot of money by because of the leak. So in order to determine any intrusions, we had a project. So any construction equipment or any object intrusions on the oil and gas pipeline right of ways needs to be captured and reported. Okay, we developed the algorithm and tested in the areas like very forest and beautiful areas like West Virginia, Pennsylvania, and all that. But what happened is they tested in Phoenix and this empty desert and rocky mountain area. You need to adapt significantly to cope up with the background. So how do we do that? Because the background is totally different. Objects are the same, but the background is different. The accuracy reduced significantly. So how do we incorporate that new contextual information or background information into the algorithm? So that's what retraining is required there. That's so we use the human visual perception philosophy itself. See, for example, a pilot who is trained in Philadelphia area or in a very forest area is being deployed in a desert area. So, see, what happens to the first few seconds, he will be lost. I mean, if he suddenly deployed in an area with a totally different background, for a first few seconds, he will be lost. It takes a few seconds to understand that now I am not flying in the area where I am used to. Now it's a different area. That means that's a retraining strategy human being uses. So why not we incorporate the same strategy for training our machine learning systems? That's what exactly we employed for retraining with a new background. The objects remain same. So it is only a retraining with a new context and background. So it's a human visual perception philosophy. There is nothing else.
Okay, there is a comment in the chat by Sudashil. Sudashil, I think he was talking about, Dr. Sudashil, he was talking about the context of the priors that you're using in the aerial imagery for the point cloud completion, the missing points, right? So he's saying if there is an aerial imagery, the occlusion would also be there for the LiDAR data. So I guess, are you using any other form of imagery other than the aerial imagery for getting the priors for the missing points?
Get the priors for removing the occlusion impact?
Yes.
Yeah, the filling up. Actually, yes. I mean, so we have previously, some information about that area in other modalities, which will be used for complete occlusion reduction. But for partial occlusion reduction, we use the object information to fill up the object. For example, if you see the tail half back side of a car, you can make up the car fully, depending upon the shape of the car which we have in our mind. So it's an initialization problem for the generative algorithm, basically. So we need to initialize the generative algorithm with some kind of information, which if it is partial, the object categorization is already, object shape is already there. If it is fully full occlusion, you have to have other modalities. Say, for example, there is a car, there is a human being, there is another animal or whatever. So that we need to fully generate and replace. But that is not as accurate as the partial occlusion filling or extrapolation there. So accuracy goes, partial occlusion removal is the best way to go. From our experience, from Nina's the dissertation, that's what exactly our conclusion basically. But definitely we can imagine when it is a total occlusion and somebody is telling that there is a car, we are making a car there, right? So we don't know. So when placing a car there, that's totally synthetic data generation basically. I mean, that's not fair. So partial occlusion, I go for partial occlusion removals. That's what exactly one of the issues. But if it is an overhanging vegetation, we can get the LiDAR data, get some information of that object. But it is but if it is a building occlusion, and we want to know, and in subsequent captures in area LiDAR, in a sequence of data captures, there is a possibility that an object flew, object was moving in that direction. And now we can generate that object in consistent, continuous sequences with the information of the object in our previous frame. That is possible. I mean, because the object information is already there. We know that, but that's a tracking at the same time, tracking and regeneration of the object which moved in that direction. There is no need for any extra data away from other modalities in that case. So there should be some information available, either in a sequence of LiDAR data, the moving objects now occluded, the data can be recreated there. If it is not a moving object, then the object is stationary, then we need to know whether it is a partial object, then we can fill it up. But if it is a stationary object on the other side of a building, then we will synthesize and place it there. That's all with the other modalities or other information or any kind of metadata information which is provided by the users to fill up. But that's basically synthesizing the data. But yeah, occlusion reduction is basically not synthesizing data. Occlusion reduction is filling up the data. So partial occlusion is the best way to generalize the occlusion reduction strategy.
So thank you, Professor. I think you have very patiently listened to all of us and answered our questions. So now I request Professor Ramya to give the vote of thanks.
Thank you, Sir Jaya. So formally, I'm giving the vote of thanks for the event of today. So first of all, thank you, Professor Asari, for being with us today and delivering a wonderful talk and enlightening us on the challenges on annotating this data set. And thanks to your research group for making, getting an unutilized data from this British Columbia and making available to all the researchers across the globe. I'm sure like many LiDAR research groups are now using your data for developing your the deep learning architecture. So thank you and your research group for the efforts in bringing up the data for the global research community. And thank you for patiently answering to all our queries. And we look forward in collaborating with you in the future. And thank you for all the participants to join today and for the maximum participation. And then thank you to Professor Jaya for coordinating and organizing this whole talk. And I guess this is a good opportunity to listen to Dr. Asari through this GRSS Bangalore and Kerala chapters effort. So thanks to all the EC committee members of Bangalore chapter and Kerala chapter for joining us with us today. So thank you all.